Hello friends, here in this video we will see a problem in which we are going to calculate the buckling load and crippling load by using both Euler's as well as Rankine's formula. Here is the question. Now when I am reading this question, whatever is there I will write that in the form of data. So here I will go on reading the question and writing that in the form of data. Now it is given that a hollow cast iron column. So first of all it is a hollow CI column has 200 mm into 150 mm outside dimensions. So I'll write down outside dimensions as 200 mm into 150 mm. Next, and 150 mm into 100 mm inside dimensions. Inside dimensions are 150 into 100. Next, height of the column is 6 meter. So height indicates the length of the column actually, that is 6 meter. So it is 6000 mm. The column is fixed at both ends. These are the end conditions given, fixed at both ends. Next, if capital E, Young's modulus is 1200 Newton per mm square. Find buckling load by Euler's formula. So this is the first part. We have to find out the load, which is the buckling load by Euler's formula, P suffix E. Then also find crippling load by Rankine's formula. So here we have to find another load by using Rankine's formula. If sigma C, compressive stress, is given as 500 Newton per mm square, and A value, that is a Rankine's constant. So Rankine's constant is equal to 1 upon 1600. So now this is the data we have from the problem. Let us try to get the solution to this problem, and we will first start with Euler's load and then go on to Rankine's load. Now into the solution part. Since it is given that at first here we have a hollow cast iron column, so I'll draw the hollow cast iron column according to the dimensions given. This is the hollow rectangular section which I am drawing. Now here we have the column section. Here are the x and y axis. Now in this column section we have material only here which I am sectioning. So this is the hollow section, and here for the hollow section the dimensions are given at outside and inside values. So here I'll write down the dimensions Now, in the problem it is mentioned the outside dimensions as 200 mm and 150 mm. So 200 mm will be the outer width, which is capital B, and 150 mm will be the outer depth, capital D. So here we have this capital B, which is 200 mm, and capital D, which is 150 mm. Next, the inside dimensions are given. 150 mm, this will be small width, small b, and 100 mm will be the small d, depth. So small b is 150, this small d is 100 mm. Now, this is the rectangular section of the column, which we have also called as the cross section of given column. Now, after that, the length of the column is given as 6 meter, and it is given that the condition is, end conditions is, the column is fixed at both the ends. So, for such a column which is fixed at both the ends, now this is the total length of column, and when over this fixed column the load is acting from both the sides, and that is a compressive load. So because of the action of this compressive load, this column will try to bend, try to buckle, since it is fixed at both the ends. So buckling or bending will start away from this fixed end, and it will stop just before the fixed end. So this much is the length of the column which is subjected to buckling, or we can say bending, and that length is called as effective length. So now in this problem, the first thing which I'll do is I'll write down, since for both ends of the column fixed, we have effective length is equal to length of the column divided by 2. So therefore effective length is equal to L by 2. That is, we are taking the length which is actually bending as half of the length of the column. Now the length of the column is given in the problem as 6000 mm. So the effective length becomes 3000 mm. Next, after getting the effective length, I'll calculate the cross section area for this column. So now, after getting the effective length, I'll say that since cross section area of given column, that will be capital A is equal to capital BD minus small bd. That is, here from the outer dimensions we are subtracting the inner dimensions to get the area, and since it is a rectangle, so therefore outer B is 200, D is 150 minus smaller b is 150 and small d is 100. So from this I'll get the value of area as 15 into 10 raised to 3 mm square. Now, after getting the area, as we have seen in the question, we have to find out both Euler's load and Rankine's load. This P suffix E is Euler's, we can say, buckling load, and P suffix R, that is Rankine's crippling load. Both buckling and crippling are same. So we have to find out first Euler's buckling load. So I'll say that since Euler's buckling load is given by P suffix E is equal to pi square E I minimum upon effective length whole square. Keeping this as the first equation. Now, if we look at this equation number 1, capital E value, it is given in the problem as 1200 Newton per mm square. Then effective length we have found out as 3000 mm. The only unknown here is I minimum, that is the minimum moment of inertia. Now for I minimum, here we would be calculating the moment of inertia about x-axis, we will get a value. Then about y-axis we will get another value. Comparing both of them and selecting the minimum out of ix and iyy, that would be the I minimum value. So here first we will start with ix, that is, therefore mi about x-axis is given by, for the given section, ix will be equal to capital BD cube minus small bd cube divided by 12. So this is the moment of inertia formula about x-axis for the hollow rectangle, that is, it is capital BD cube minus small bd cube divided by 12. So putting the values here, therefore ix will be, now here if we see, capital B is 200 and D is 150, so it is 200 into 150 cube minus small bd cube, small b is 150, small d is 100, so 150 into 100 cube divided by 12. So after we calculate this, we will get the answer of ix as 71.88 into 10 raised to 6 mm raised to 4. So this is the moment of inertia about horizontal axis, that is x axis. Now we will calculate the moment of inertia about y axis. Since mi about y axis is given by Iyy is equal to, now for Ix we had written BD cube, capital BD cube minus small bd cube by 12. For Iyy I will use dB cube by 12 because that is the formula to get moment of inertia for a rectangle section about y-axis. So it will be capital dB cube minus small dB cube divided by 12. So putting the values here, now capital D is 150, B is 200, so 150 into 200 cube minus small d is 100, small b is 150, so 100 into 150 cube divided by 12. So therefore Iyy value comes out to be the answer which I have, 43.75 into 10 raised to 6 mm raised to 4. Now these are the Ix and Iyy values, and out of them we want the minimum value. So on comparison, it is clear that IYY value is less, which is 43.75, 10 raised to 6, whereas IXX is 71.88, 10 raised to 6. So I'll say that since your IXX value is greater than IYY, so therefore I minimum will be IYY because it has less moment of inertia, and when you have less moment of inertia about that axis, the column will start bending, that is, it would start bending about the y axis. So here is the value of I minimum. After getting this I minimum, I'll say that putting all values in equation number 1 to get the Euler's load. So therefore, put all values in equation number 1. So we have Euler's buckling load as pi square, E is given as 1200, I minimum 43.75 into 10 raised to 6 and divided by effective length whole square. Effective length was 3000 mm square. So now we are getting Euler's load, and my answer is, it is 57.57 into 10 raised to 3 Newton, or if I divide it by 1000, that becomes 57.57 kilonewton. So this is the first answer, answer number 1. Now after finding the Euler's load, the next thing is to get the Rankine's crippling load. So that is the second part of the problem. So I'll say that now therefore Rankine's crippling load is given by P suffix R is equal to sigma C into capital A upon 1 plus small a into effective length upon K whole square. I'll keep this as the second equation. Now if we look into this equation, the value of sigma C is given in the problem as 500. Capital A is the cross section area we have calculated. Small a is the Rankine's constant, which is 1 upon 1600 given. Effective length and K values. Now we will go for this to calculate these values. Next, I'll say that K is called as the radius of gyration, and first thing which we would do here is to solve the denominator. That is, first I'll say that therefore, since K is called as the radius of gyration and here I require K is equal to, first of all, that is root of I minimum upon the cross section area, and here I require K, this will become K square. So from this, K square will be I minimum upon cross section area. Now I minimum we have found out just now, that was 43.75 into 10 raised to 6 divided by the cross section area 15 into 10 raised to 3. So here we have the value of K square as, it is 2916.67, and this value be in terms of mm square. So now after getting K square value, I'll calculate this denominator completely and then I'll put it in equation number 2. So therefore I'll say that complete denominator, which is 1 plus small a into effective length square upon K square will be equal to, I'll find this value, 1 plus Small a is given as 1 upon 1600 into effective length is 3000 square divided by k square, we have got the value 2916.67. So from this complete calculation, I'll get the denominator as 2.928. Now this is a constant value, so it has no unit. Now I'll put all values in equation number second to get Rankine's crippling load. Therefore, put all values in equation number second. So we have Rankine's crippling load as, here it was sigma c into capital A. Sigma c was given in the problem as 500 into capital A, we have found out 15 into 10 raised to 3 divided by the complete denominator we have calculated separately, it was 2.928. So from this, if we calculate, we will get the Rankine's crippling load as 2.56 into 10 raised to 3, it is into 10 raised to 6 Newton, or 2.56 into 10 raised to 3 kilonewton. So here is the second answer. We have found out the Rankine's crippling load. Now if we see in the problem, here we had a column which was fixed at both the ends, and the question was to calculate Euler's load, which was Euler's buckling load, and Rankine's crippling load. Because of both of them, that is Euler's and Rankine's load, the column will buckle. It is definitely going to buckle, means it will bend in this way, which I have shown in the diagram. So we have to find out the value of load at which it was buckling, and that values we have found out. First, we had calculated the Euler's load, and that value was 57.57 kilonewton. And next we had calculated the Rankine's load, which is 2.56 into 10 raised to 3 kilonewton, and with this we have solved both the questions, and here we complete the problem.